Okay. So looking at Hux, doing pretty decent with the assignments and stuff. Good. Looks like everybody's logged in. Good, because I literally just got the email about 15 minutes ago that I have to put the report in for tomorrow. So that's good. Any major issues, problems with it? Okay. All right. So gonna be doing a little more math today. So last class we talked about some basic graphs, bar charts, pie charts, which works really, really well for qualitative data. So we're going to move into how we can use similar things for quantitative data. So one of the things that you typically see, and a lot of people call them a bar graph, is what's known as a histogram. A histogram is very similar to a bar graph, but it is based on qualitative or quantitative data instead of qualitative data. So we're going to look at how to be able to construct frequency distributions, which will lead into how to construct histograms. And understanding histograms will lead into how we can start doing the bell curve and all that other stuff later on down the line. So let's look at what a frequency table is first. So typically when you collect your information, you're going to have a table of data like you see here on the left. So with the heart rates of all per minute of 50 students. So you collect all the raw data and then you have to organize it into something that you can use. And that would be our frequency distribution. So in this frequency distribution, they broke it down. They started at 57, go to 66, and so on and so forth all the way up. Why do you think they started at 57? Yeah.
Nobody was below that.
Nobody was below. What's the lowest heart rate? Yeah, that's the smallest one I found when I was just scrolling through it real quick. So why not start at 62?
To keep even intervals.
Okay, so why not start at 60? So you can start to see how when you're looking at a frequency distribution, the way we design it and set it up, there is some flexibility. Okay, there's no reason to start at 57. Okay, we could have started at 60, we could have started at 62. However, does that change the number of students in each category? If we started at 60 and went from 60 to 69 instead of 57 to 66, we'd still have 10 in each one, right? But it would change possibly some of those groupings. So when you give your information, you need to start looking at how you want to organize that information. How do you pick it so that you have all the information in there? So yes, 57 was chosen because there's nothing below it, but that number was chosen arbitrarily at the beginning. Okay? So that's one thing. The rest of it comes into play is like, well, why are we doing 10s? Why do we do 57 to 66? Why couldn't we have done 7 in each one, or 8, or 20? Like it doesn't, like, so there has to be some way to organize it and keep it semi-standard, and still allow us to see the information correctly. Because you don't want to go too small, because then every category basically has like 1 or 2s in it, and you really don't see anything. You don't want to go too big, because then 1 or 2 categories are going to have everything in it, and you're still not going to see things. The goal of organizing the data is to start to see a pattern, to get something, get information out of it, to understand what's going on. So if we look at this, what are some of the information that you can get just by looking at the table on the right? Yeah.
Majority of people are between 77 and 86 people.
Yeah. So it's like you see that quickly, and it seems to be pretty even around it, right? We had 10 on one side, 5 on the other, 2 and then 1. So it kind of makes a nice little curve, which we'll see in a little bit when we do the histograms. All right. So first thing we have to do when we're looking at a frequency table is you have to determine how many classes there should be. So a class is the breakdown of the distribution. So when we're looking at this, the first class is from 57 to 66. Second class, 67 to 76. Okay. And that's arbitrary. You can choose however many you want. If you have a ton of information, maybe making them a little bigger might be fine. Okay. But if you have it too small, you're not going to see enough information. Too much, you're not going to see information either. So you have to look at your data and decide which way is going to show you the information in a way that you can use. Okay. Next part. Once you've determined your class width, we need to figure out, once you determine how many classes you want, how many groupings you want, we have to decide what our class width is going to be. So the class width actually has a formula. So as I said, we're going to get into some math and do some actual calculations. So your class width is your minimum value, or your maximum value minus your minimum value, divided by how many classes you want. All right? So I will come back to the slide in a second. What's the minimum value? I think we said it was 62, right? What's the maximum value?
98.
Yeah, I think actually right next to 62 is 98. And I think that's the biggest one. All right, so we got 62 and 98. That's the minimum and the maximum value. So we've got 98 minus 62. And how many classes do I have? How many classes did they pick? They chose 5. So we're going to divide it by 5. All right. So what's 98 minus 62? All right. And 36. And we'll divide that by 5, and we get 7 and a little bit, right? So whenever you're going to have, it's a rounding. So what is it? 7.2, I think, actually. Yeah. Whenever you're going to have to round, in this situation, you always want to round up. Because if I chose 7 for my class width and I counted out 5, I'd only get to 35 possible numbers, and I'd have some left over at the end. So you'll always want to end up rounding up in this situation. So I would have rounded up and done class width of 8. But they did a class width of 10. So is this a properly done frequency distribution based on this concept? Did they do it right? No. They did it by tens. They started at 57 to 106. So they did 106 minus 57 and divided by 5. So they ended up getting 49, which is approximately 10. So they just chose a smaller number and a higher number to be able to do that, to break theirs down. But if you're looking at the data, we would want to do class sizes of 8. All right. So we're going to look at it. So if we wanted to do class sizes of 8, because that's what we determined here for this problem. My smallest number was 62, correct? So the lower limit is the smallest number that we can include. Okay, so let's start off at 62. So we're going to go 62 and we're going to have a class width of 8. So what's the upper limit going to be? No, for this one class. So remember, my width is going to be 8. So if I'm starting at 62, where is my upper limit going to be? Where's the end point of this class going to be? Everybody agree with 70? Okay. I want you to count from 62 to 70. And tell me how many you counted.
Let's see.
How many did you get? 62, 63, 64, 65, 66, 67, 68, 69, 70. How many did I get? 9. Not 8. So my class width is 9, not 8. But I wanted a class width of 8. What was the mistake we made?
Rather than from 62.
Right. When you count, a lot of times you don't count one of the endpoints. You go to 62, 63, 64, 65. But when you're looking at these, are we going to put 62 in this category? Yeah. So 62 counts. Are we going to put 70 in this category if 70 was there? Yeah, 70 would count. So therefore, the way I just did this, my class width is 9, not 8. So when you're looking at doing your calculation, you're fine. You did exactly what I expected you to do. You did 62 plus 8 and got 70. You actually have to take one away from it because we're counting the endpoints. So it'd be 62 to 69. And if you think about it, if we go back and look at what this was, we said 57 to 66 was how many? That was a class width of 10. But it's not 57 plus 10. Okay. So this is one of the quick little mistakes that's really easy to make. So when you're doing your class widths, when you're trying to find your lower class limit and your upper class limit, this would be my lower class limit. And this would be my upper class limit. When you're doing the calculation to do for class width in there, just remember your class width is how many numbers you're counting in there and not the difference between the two numbers. Okay, because the difference in this case is 7, but my class width is 8 because there's 8 numbers that would be a value in there. So my first class was 62 to 69. What's my second class going to be? What would my second class start off at?
70 to 77.
So I'm going to start off at 70 and I'm going to go to 77. Good. Next class. Okay. How many classes did I need? How many classes did I say we were going to have? My class width was 8. My classes were 5. I'm going to have 5 classes. All right, so we've got 3. What's the next one? I need 3, I think. The nice little trick. Remember what I said? It was always one less. So instead of adding 8, add 7. This way you don't have to physically sit there and do the counting, which I've seen people. I literally look, I've seen people with the biggest counting. Yeah, just add one less. All right, we've got 4, so I need 7. I need 5, right? So I need one more. What's the last one? Okay. What was my upper number? 98. And my lower number was 62, right? Will all those numbers fit in these classes? Yeah. So we're good. That's a good class. We start off exactly where my lowest number is, and we're higher on the upper end. Is that okay? Yeah. Why are we higher at the upper end and we didn't end exactly at 98? Yeah. We had that little rounding thing, right? So if we had done 7 instead of 8, I won't make you do the counting for this one. It'd be 62 to 68, 69 to 75, 76 to 82, 83 to 89, 90 to 96. I got 5, right? Can I fit all the numbers in there? No. That's why we always have to round up. Okay. Even though 7.2, the way you've always been taught to round, you round down. In this situation, because of the way we have to work on it, you always have to round up. Okay. Because otherwise, your numbers won't fit. You either have to add another class, and then in which case we have 6 classes and not 5, or we have to round up. Okay. Okay. All right. So we find our class width, and we choose the number of classes, so that's arbitrary. Find my class limits, we take that class width, and we're going to start with the lower one, and we're going to go up that number every time. So we're going to go up 8 numbers, including the one we started with. So in this case, you're going to add 7 or 1 less than what your class width is. The last thing you're going to have to do is we need to figure out our frequency of every class. So we did 69, 70. Oh yeah, there we go.
Oh, there we go.
I didn't actually write much else up there though. So write this down. I'll blow up this in a second, but I want you to make sure you have the classes written down somewhere. And then I'll make this bigger.
It would help if the numbers were in order.
Oh, of course that would help. So when you're doing these, just do tally marks. Okay, don't try to go through and look for all the ones in there. Just every time you hit 77, put a tally mark in that box. Okay. All right, everybody good with the classes? Okay, I'm going to make this bigger. There you go. A little easier for you to see it. All right, we got them? You need a minute to? If you were doing this in the real world as a job board of RELs, you're going to be using technology to do a lot of this. So typically all this information would be in a spreadsheet, which you can sort and count and everything else like that. So, which is what I was actually trying to do a second ago, but when I copy and paste it from the book, it actually just copies with one line, which doesn't help me very much. All right, so how many from 62 to 69?
4.
How many from 70 to 77? 78 to 85.
21.
86 to 93. 94 to 101. Does that add up to 50? 31. No. That adds up to 40.
That's the table that's 5 by 8.
It does say 50 students, right? Yep, there's 50 there. Okay, who's got different numbers? Because something's off. Yeah.
5, the first one, 11, 26, 5, 2, but I am missing one, I think, so.
Yeah, I think.
36. Okay. Okay, yes, that's 49. Yes. That's supposed to be 6?
Yeah.
Okay. Okay. We got 50. Not totally sure it's right because I didn't count them up, but we'll go with it. It's 50. Does this chart look drastically different than the one they did with the 10? We can actually see them both. So that's the 10, that's ours. Is it drastically different? No. Do you see basically the same? Because remember, the goal is when we're starting to look at taking and moving into charts and graphs and things like that, is to start to look for patterns, to look for information, to be able to display it in an easier way for people to read, right? It's a lot harder to read if I give you that list of 50 things. Even if I put it in order, it's still not that easy to read. So the chart's meant to actually simplify it down for you to see patterns and for the end user to have some better information. So is the pattern similar? Yeah. So changing from 10 to 8 really didn't change my pattern too much. It's pretty much the same results there. You still see it. It's still clumped right around that middle section. Our middle was going from 78 to 85. Theirs was going from 77 to 86. So that's where those couple extra ones came in. But you still have that general curve to it. So not drastically different. All right. So you can start to see a general idea of how to actually do charting like this. Okay. Like I said, typically all your data would be in some kind of a spreadsheet, Excel, Google Docs, whichever one you want to use. Will basically do the same similar things. And those programs have built-in things to be able to sort the data, to count the data, to put it into these type of charts. But if you're doing this in a real situation, you're probably going to be dealing with thousands of data points, not just 50. Okay, so the numbers become a lot more complicated in that respect. All right, so let's look back at the original table that they gave us so that we can start to see some of the other concepts that we can deal with as well. So we have our frequency distribution, which we've already looked at. So this, we're going to go back to the one with the 10s just because all the tables are already created and I don't have to redo them all. So we have our frequency distribution, but we talked about last class was when we change things to percentages, a lot of times that gives us a little better way to compare things. Okay. So in that respect, that's what's known as a relative frequency distribution. So our frequency distribution is just the count. Our relative frequency distribution is the count divided by the totals. So our numbers are going to be in terms of percentages. So in this case, you can see that 2, and we divided it by 50 because there's 50 values. So we get the 4% or the 0.04. Remember that percents are always 2 decimal places. So 0.04 is the same thing as saying 4%. 0.20 is 20%. That's 64%, 10%, and 2%. So while looking at it in terms of percents doesn't give me any more of a pattern, the pattern's still the same. It does allow me to tell people what's going on in a way that they understand. Because most people, again, have an understanding of what a percent means and knows it's out of 100. So in this case, we did it out of 50. So if I said 32 out of 50, they're not going to have as much of an understanding as if I said 64%. Okay? So all the relative frequency does is it takes the amount that you counted and divide it by the total values that you had. Does that make sense? Simple enough? Okay. Cumulative frequency is where we add up all previous categories or all previous classes. So our frequency is here, our cumulative frequency goes over here. So for the first one, our cumulative frequency is the exact same as frequency. The next one, we would add the previous 2. So that's how they get the 12. The next one, they would add those 3. So 44, 49. And your last class should have the exact same as your total. So in this case, we had 50 values. So my last class in the cumulative frequency should be 50. What's a good use case of a cumulative frequency? Why do you think that's useful? What's a very simple case of why it's useful?
It can help you to make sure you got all your data.
There you go. That's one of them. That was the first thing I did. Everybody's when they were adding up, like add them up. You have the cumulative frequency. You've already added them all up. So that should be your total, right? So that's one really good use case of a cumulative frequency. Another one is a lot of times we want to say like this is the value underneath something or above something when you're trying to group categories together. So I could say that there's 44 people that have below an 86 beats per minute heart rate. Like that's easy to have. We now have that data right there without having to go through and add up those totals. The other one is because the cumulative is there, it makes it, we can do a quick subtraction to find between categories if we wanted to. So like if I wanted to find the difference between 96 and 67, like how many years between that, I could just do the 49 minus the 2 and get 47. So you can look at quickly doing some calculations in that respect. So cumulative frequency is probably the least useful one. Well, relative cumulative frequency is probably even less useful. But it does come up every so often. So. And then the other one that I just said was even less useful is the cumulative relative frequency when we just add up the percentages. So just like we had with the frequency table, we can add them up to get the totals. The cumulative relative frequency is just adding up the percents. And your last one should always come out to be 1 or 100%. Make sense? Okay, let me shrink this a little. Maybe. Okay. There's 100 heights here. How many classes do you think we should do? So remember, classes is arbitrary. That's you get to basically pick how many. How many classes do you think would be good to do?
Five.
5. Okay, so we're doing 5 classes. Good. All right, find me my class width. And no, they're not in order either. I'm not going to make you do a whole frequency table on, don't worry. So the two things you need are what? Highest and lowest. So find the highest one, the lowest one, and then do the calculation to find my class width. I'm suspecting you had the answer. That's why I was suspecting. Unless you had a question. Okay. I'll give you one more minute.
How much of this class will be sorting through? Like,
Nothing.
sorting
Very
through-
little. Don't worry.
Getting scared.
No, very little. This section is. The vast majority of this. We will be doing some calculations and stuff like that. There will be a lot of formulas and things like that later on in the semester, but I'm even going to, some of them, I'm even going to give you calculators online to actually be able to use to simplify them down. So, all right, what's the smallest one? Go ahead. 56.6 is the smallest. The biggest one is 71.6. There's a 55.2? Oh, you're right. I like those are the two I got. So like I missed that one. Good catch. Is there one bigger than 71.6? Okay. All right. Awesome. Okay. So for my formula, 71.6 minus 55.2, and we're going to divide that by 5. What's 71.6 minus 55.2? Was it? 16.4. Let's see if I can actually write correctly today. Divide that by 5. I get 3.28. So my class width is going to be what? Okay. I could do 4. I could do 3.2 or even 3.5. I mean 3.3 or even 3.5. So why in this situation can I do 3.3 where in the last one I could not? Go ahead. Yeah.
There's decimals for these ones.
Yeah, I have the decimals. Okay. So when you're rounding, you always want to, you can round to whatever the decimal places they give you in the problem. Since I have decimal places in it, going to 3.3 would be fine because I still would be able to include all the values that are in the problem. Okay. Going to 4 is fine. There's nothing wrong with going to 4 and keeping them as whole numbers. It's not that big of a deal in this situation, but that just gives you a little bit more options. That's actually the why I picked this data set, because I wanted to show you one with decimals, because not everything is always going to be whole numbers. Okay. So in this situation, let's actually do the 3.3 just because I want you to actually see the decimals. So where do you want to start? We got 55.2. So this is one of those ones, depending on the number you choose, depends on how you want to start. Let's say we chose the 4. I don't want to start at 55.2 because then I have decimals. If I do 4, let's start at 55. We'll do 55 to 58. You don't have to start at the smallest number. Okay? You can start lower than that. As long as whatever you break down your class with, your end has the biggest number. Okay? Since I'm going up to a class with the 4, I'm pretty much going to be spread out there, so I'm probably going to be fine. So if we did a class with the 4, what's the next one going to be? 59 to, what was it? Yes. Yep. Okay. The next one would be 63 to 66, 67 to 70, and then 70 to 73, right? Oh, you're right, 71. Okay. Is that how you do it? Does that make sense based on what we've done previously? Okay. Where would the number 58.8 go?
Want to round it up to 59? Would that affect the-
That would mess up the data. So you can see a problem now the way that we're doing this by breaking it down and looking at it as a class as a 4. If we're doing whole numbers, you lose those decimal points in the middle, right? So if we had said, okay, well, this is from to 58.9, my class width is actually 4.9 now, not even 4. So we would actually, what I would actually have done in this one is I would have done 74. I would have done 55 to 57.9, and then I would have gone 58 on this case. You want to make sure your table fits your data. Since we have a decimal place, we need to have a decimal place in the actual data to make sure that works. Okay? So you sometimes have to manipulate it to make sure that it works correctly. The 3.3 wouldn't have had that problem because we were already dealing with the decimal point to begin with. So you still could have started off at 55 and done 3.3 going up and then 3.3 from there. You just have to make sure that when you jump to the next class, you're only jumping whatever your decimal point is at that point. Okay? Does that make sense? Well, I like this problem because it's like, if the last one was all whole numbers, so it's like you get that stuck in your head. It's like, this is the way that's going to look. But then when we deal with some extra digits in there, it can become a little more complicated. Okay. All right. A histogram. Has anybody seen a histogram before? So this is a histogram. What does it look like? It's just like our bar charts. What's the difference between this and a bar chart? There's a few. Give me one. Would you like to see a bar chart again? Let me see if I can find it real quick. Yeah, we'll use this one. All right, so here's a bar chart. What are some differences between these two? Ignore the fact that it says Susan, William, Beth, and Rob. Those could be numbers too. That's not that big of a deal. What are some of the distinct differences? This is like one of those pictures. Spot the differences. Yes.
They go in ranges instead of values, like just one value.
Okay. What else?
The bars are connected.
The bars are connected. Why do you think the bars have to be connected? Think about what he just said. They go in ranges, right? So why would the bars be connected?
One bar picks up where the other bar leaves off.
Yeah. That 66.5 is right between the two classes, right? So the data from one kind of blends into the data from the other one. It starts off right where it left off. So that right there, that's the biggest piece of a bar of a histogram. Okay. The histograms, the bars have to be touching. The histogram, the boxes down below are not beneath the actual bars. They're a range of values. So if we look at, this is the frequency table that we were dealing with before. Notice how my range went from 57 to 66. Notice how I do not have 57 or 66 anywhere on this table. Your histogram has to be the breakpoint between the two values. Okay? Because if I made this 66 instead of 66.5, where is the value for 66 going? In this bar or this bar? We wouldn't know. By making it 65 or 66.5, that is not a value that would have occurred in my data set. So therefore, I do not have a problem of it being evaluated specifically on that point. That make sense? Okay. So you always go the halves between them. So in this case, it was 56.5 to 66.5. Now, let's think about this for a second. What's my class width for that? What was my class width for this frequency table they gave me at the beginning? 10. What's 66.5 minus 56.5? It's 10. So the class width we use to create the frequency table. However, it is actually the width of the bar in the histogram. Okay, so that's that connection back to it. So those should be exactly what your width is when you subtract those, because we're not counting either of those numbers. We're looking at between those values. Okay. So let's see if I have it on here or not. No, I do not. That's okay. So in this one, this horribly long list of values that we did. If I did to, what was that? We did what? 4, so 58 to 61.9. No. 60.9. What would be the breakpoint between these two classes? If I had a histogram, what would be the bar? What would be on the bottom of the bar for the? What would be the first number?
Or the first
number for,
The first number for the bar. So when we're looking at the bar here, remember it has that first number and that number? So what are those two numbers? What's the first one going to be? But can I make it 55? Yes. I go one extra decimal place. I'm looking at the hundredths when I'm doing my half and not the tenths in this case. So it'd be 54.95. And then the other one would start at 57.95.
So you just add one decimal point from whatever
Yes.
the data is.
Yep. Yeah, you always go, and it's always a half. You can always use the 5. So you're basically going down by that half there and then up by the half on the other side. Okay. All right. The official definition of a histogram. It's a graphic representation of the frequency or relative frequency. So the histogram that I showed you was the frequency, but you could easily have made it a relative frequency by just doing the percentages there instead of the total counts. Either one of those values work. The horizontal scale represents the classes of the quantitative data. Notice how it's quantitative data. This can only be done with data we can do calculations on. All right, we cannot do calculations on names and things like that. Even though we possibly could put them in order, we can't do calculations on it. So it has to be quantitative data. And the vertical scale represents the frequency or relative frequency of each class. Just like when we're doing a bar chart or a bar graph, the frequency going up should be equally marked. So in this case, it was going up by 5s. Or if it was percentages, we went up by 10s. Either way, they should be equal, and it should start off at 0. Your horizontal one does not have to start off at 0 because our data does not necessarily start off at 0. Your horizontal one is going to start off with wherever your data starts off. All right, so these are histograms without anything actually added onto the bottom. Okay. So these histograms have some information with them. So when we're looking at a histogram, we can start to look at patterns. So the histogram we just looked at, this one, it kind of looks curved where the peak is in the middle, right? That's not always the case. You can have histograms that are skewed. You can have them, this is symmetric, where that makes a nice little curve. We can have it skewed this way, or we can have it skewed this way. Now, if I was to ask you, and the words weren't there, and I probably should have erased them. If I was to ask you what this skewing was, the one in the middle here, how would you tell me that was skewed? I know it says underneath, but how would you, if you didn't see the name, how would you tell me that's skewed?
I would say it's super.
Correct. You would look where the biggest the bump is, right? Okay. There's no way I'm going to be able to explain to you why it is the case completely. I'll tell you, but you might not understand it until we get later on in the semester where you get a lot more information. It's skewed left because the values on the bottom will pull the mean that direction. So when we start talking about mean, median, and mode down the line, that's why it's skewed left and skewed right. So skewing left means that I'm pulling the average to the left of center. So these values down here is going to influence the mean or the average that direction. And that's why it's to the left. Where this one, those higher values over here are going to pull the mean that direction, is why it's skewed to the right. So when you do your homework, because this is on the homework for this section, you're not looking where the hump is, you're looking where the tail is. Okay? So if the tail's on the left, it's skewed left. If the tail's on the right, it's skewed to the right. Does that make sense? Yes.
You mentioned these different types of like results on these histograms.
Yeah.
In the homework, it mentioned stationary and non-stationary graphs. I was just curious if that's like a similar thing, like it's just explaining a trend. It was under 2.3, I think.
Oh, hold on. Oh, I think that was with time series.
While we're on the topic of
No, that's fine. Yeah, no, that's totally fine. I want to see what they meant. I'm literally trying to figure out what they're actually talking about in it, which is one of the reasons sometimes I don't like Hawks. Okay, so the difference between a stationary process and a non-stationary process. In a time series, a stationary process, the time series varies around some central value and it has approximately the same variation over the series. So it's very similar as it's going on. Where a non-stationary process, the time series possesses a trend. So, for example, the temperature over time would be non-stationary as it's increasing over time. There's a trend there. Where if we're looking at minimum wage, for example, it's basically stayed the same. That would be stationary. Okay. Good question. And you're right. Totally didn't talk about that. All right. So does everybody understand the top one? The top list here makes sense? Uniform, if we're going back to that stationary and non-stationary, uniform would be stationary. It looks very similar going across. All right. Bimodal and multimodal, you have multiple peaks. So bimodal, there's 2 peaks. Multimodal, there's multiple peaks. And that's going to lead to mode, which we're going to talk about when we talk about mean, median, and mode in chapter 4. Okay. All right. We have one more type of graph. Has anybody ever seen a stem and leaf plot? A long time ago. All right. So a stem and leaf. So if we're looking at this, okay, this is known as a stem and leaf plot. If I took this and I changed it to look like, let's actually try to make it straight up and down, like that, what does it look like? Bar graph. Okay. So a stem and leaf plot is just a way to organize your data. But by organizing it in this way, we can start to see patterns that we saw in our histograms and our bar charts. And leaf. So this value right here, that's 67. The next one, so this table, this one right here is 67, 69, 68, 65, and 62. So the stem is the first digit, the leaf is the second digit. Okay? Your stems are typically just the biggest digit in it. Your leaves can actually be multiple digits. Most times it is not, but it could be. So it's always the stem first and then whatever the leaf is after that. So that's how you get 67, 68, 69, 65, 62. It's also a nice way to organize your data as you're writing it down. So if you think back to that first problem when I wanted you to sit there and count all 50 of those, if you had originally put it into a stem and leaf plot, you now have organized your data. It makes it easier for you to do those counts. What's the class within this? What is the default class with any stem and leaf plot? Yeah, 10. What's the ones that are going to go in the sixes? 60 to 69. The 70, 70 to 79. It's grouped by our place value system. So it's grouped by tens in this situation. Okay. Normally a stem and leaf plot, once you put it there, should be in order. Okay. So the top one should not be listed like that. It should be listed as 6 and then 2, 5, 7, 8, and 9 of those are horrible rate of 8, like that. It should be in order. It doesn't have to be, but it should be. Okay. So there's the ordered stem and leaf plot, just basically putting them all in order. One. This is an example of a stem and leaf plot that is not based on tens. This stem and leaf plot is based on what? What would be my class width for these? Yeah, 100. We're looking at it in terms of, remember, my stem is always the first digit. So in this case, I got the 0 and the 1. And my leaves are a little bigger. Okay. You can have, so like if, for example, in this one, I could have the stem be 10 and the leaf be 9. That digit right there would be 109. That is possible as well. So it's really depending on what type of data you have and how you're organizing it. So in this case, the majority of my data is single digits. I mean, not single digits, in the tens. So organizing my leaves as in the tens place makes more sense. In this case, they decided to make them all in the hundreds. So doing it in the hundreds case made more sense. However, whenever you're looking at it, it's always going to be the same. So it's always going to be multiples of 10 when you're looking at it. So tens, hundreds, you could technically do thousands. I will tell you right now, the chances of you seeing something like this, like a stem and leaf plot like this, is slim. But I found it interesting because it's always one of those questions that comes up of what happens when you get higher and higher numbers. You still can do a stem and leaf plot. You just have to recognize that 97 is not part of 99 because you do not put commas between them in a stem and leaf plot. You just write the numbers. The other type of stem and leaf plot we have is known as a back-to-back stem and leaf plot. Since football season is now officially over, it is now baseball season. So this is showing the home runs hit for Babe Ruth and Barry Bonds. So when you're looking at this stem and leaf plot, again, all this is supposed to give you the data in a visual way so you can start to see patterns. Okay? So when we're looking at this, the nice thing about a stem and leaf plot as compared to like a bar graph or a histogram is you actually still have all of the data there. So I can pick out and pull out individual pieces of information and still see patterns for me. So what is a pattern you see forming between Babe Ruth and Barry Bonds? Or what's a pattern you see on one side? Yes.
Bonds is the highest percentage.
Yep. Bonds has that 73 up there. So he is officially the home run, single season home run record holder. You gave me one. What's another thing we see?
Most commonly in the 30s and Ruth was most commonly in the 40s.
Yeah, so Bonds was around 2, 3, and 4. The 20s, 30s, and 40s was where most of his seasons were. Ruth had a lot of seasons, more in the 4s. He had a lot of single-digit seasons. Everybody know why Ruth had a whole bunch of single-digit seasons? Yeah, he pitched. Those are the years he was pitching. That's what makes Ohtani so amazing. Like, he can do it at the same time. It's
Andy can
absolutely.
steal 50 base.
Yeah, he's crazy. He literally is crazy. What's that 73? If you look at that 73,
That would be a big old outlier.
yeah. So we're going to start to look at what's known as outliers, and there's actually some definitions for those when we start looking in chapter 4 as well. But an outlier is something that's drastically different from all the rest. So before that season, his biggest numbers was 49. So to have that big of a jump was a drastic change in it. Where Ruth was pretty consistent. Yeah, he had the 60 there, but he had 59, 54. There was other ones around there. So the 60 wasn't necessarily out of the realm at that point. Okay. So that's where we could start to look at stem and leaf plots and bar charts and histograms to start giving us that visual representation of our data. All right, one more graph and then we're done. This is known as a dot plot. It is similar to a stem and leaf plot where it shows you every single data point. So, except every one of these dots represents one value. So this is like a histogram on steroids. Every single bar is one value. Okay. Yes, it was a total jab at Barry Bonds. So if we're looking at this, 65 happened once. 66 happened 3 times. 67 happened twice. You can see every single data point in there. So when we're looking at our class widths and stuff, this is a class width of 1. This only works when you have a bunch of data and a relatively compressed area, so you can still see kind of patterns with it. Okay? Like this wouldn't work if every year was a different value and it was all just one line. That wouldn't help you very much. But we can start to see some patterns forming in it. So this is known as a dot plot, and it does give me some more information. Like that season of 38 was a little bit of an outlier for the Chicago Cubs.
I hope that wasn't 162 game.
I don't know. I don't remember when the Chicago Cubs lost. Which year was it? They won 116 games, that high one. Oh, I didn't even put that one on there. Was it 1906? Oh, it was because it was pre-expansion bid. Yeah, I can't find, like, it doesn't. Yeah, it doesn't tell me when. That one they don't give me. They give me all the rest of the data. Yeah, I can't find it quickly, and I'm not going to keep looking. So, all right. Those are our graphs. We're done with chapter 3. We move into chapter 4, more calculations on Wednesday. See you later.